Welcome to AI Paper Podcasts. We are jumping straight into a truly foundational paper today. It's called OmniVGGT, Omni-Modality-Driven Visual Geometry Grounded Transformer.
And if you only have about a minute, here's the bottom line. OmniVGGT introduces this really novel framework that basically solves the input flexibility problem for 3D foundation models.
Right.
It uses your standard RGB images plus an arbitrary number of extra geometric cues, things like depth maps or camera poses, and it unifies a whole bunch of 3D vision tasks at the same time.
And the architectural breakthrough that makes this possible is something called the Geo-Adapter. It's incredibly lightweight. We're talking only 26.8 million new parameters on top of the massive VGGT model. And this adapter uses these specialized zero-initialized convolutions, this zero-conv mechanism, to safely inject all this geometric data without, destabilizing the whole thing.
And the payoff is just huge. OmniVGGT gets state-of-the-art results across the board. When you give it depth data, it hits near perfect 99.9% accuracy on benchmarks like Bonn and NYU V2. And crucially, it's also incredibly efficient getting the best pose estimation scores while being about 30 times faster than older methods.
Okay, so let's really unpack the motivation here, because this feels like a huge necessary step for 3D AI.
Yeah.
We've all seen how LLMs, large language models, just completely changed NLP.
Yeah.
And the goal for models like the original VGGT was to do the same thing for 3D perception handle depth, pose, view synthesis, all inside one giant model.
That's right. But there was always this massive bottleneck. The critical limitation of the big models in this space, like VGGT or even DU to 3DR, is that they are fundamentally built for RGB-only inputs.
They just treat images as the one and only source of truth for understanding a 3D scene.
Exactly.
Which seems so inefficient when you think about the real world. I mean, autonomous cars have LiDAR point clouds, right? Your phone's AR apps often use RGBD sensors with depth maps.
And in robotics, you almost always know the camera's precise calibration, its intrinsics, and its pose in the world.
So all these geometric cues, the depth, the camera parameters, they're often just sitting there ready to be used. But before this, the models were just too rigid to use them flexibly.
Totally. You might get a model that could handle one extra input, maybe two, but nothing could handle an arbitrary number of them. A system that works if a cue is there or if it's not, or if you only get it for a few frames.
So that was the mission. Build a model that can take 0 cues, 1 cue, or a whole bunch of them, and just seamlessly integrate it all. So if that was the problem, how did they actually crack it?
Well, the solution really comes from how they handled the basic conflict between the different types of data. Depth is, a dense per pixel local thing. It tells you how far away each point in the image is. But camera pose, that's a global attribute. It's a single matrix that describes the entire camera's position for the whole frame.
Right, and trying to just jam a global matrix into a huge transformer's feature space, that sounds like a really bad idea. You could just destroy all the carefully pre-trained weights.
That's the danger, absolutely. So they needed a really controlled, structured way to introduce this geometric cheat sheet. They solved it with the Geo-Adapter, which has two parts, a camera adapter and a depth adapter.
Let's start with the hard one, the camera adapter for the global stuff. This is where that famous zero-conv trick comes in.
Precisely. So first, they take the raw camera info, your intrinsics like focal length and the pose, and they parameterize it into something more manageable.
Okay.
So the complex rotation matrix becomes a rotation quaternion, and you have your translation vector and the field of view. It just makes the global data much easier to handle.
Let's pause there for a second. For anyone listening, why a quaternion? Why not just use, say, standard rotation angles?
Good question. The quaternion is just much more stable. It's a way to represent 3D rotation without running into problems like gimbal lock, which can happen with Euler angles. For a model that needs to smoothly learn 3D poses, it's just a more robust, compact choice.
Got it. Okay, so they processed this feature vector through a camera encoder. Now for the magic, that zero initialized layer. Why is that trick so important for these global tokens?
The auxiliary camera tokens get passed through this zero initialized convolution layer. And you can think of this layer like a valve that's completely shut at the beginning of training. So when you start, the influence of that extra geometry is exactly 0. The network then learns to gradually open that valve, to slowly blend in the geometric data without shocking the system. It guarantees a stable, progressive injection.
That's brilliant. It's basically a built-in stability guarantee. So how does that compare to the depth adapter, which is handling that dense pixel-aligned depth map?
The depth adapter is way simpler structurally because the depth map is already spatially aligned with the RGB image.
Right, they match up pixel for pixel.
Exactly. So they just normalize the depth map, concatenate it with the mask to show which pixels are valid, and then run it through a very simple single-layer convolutional encoder.
And here's the key difference, right? Unlike the camera tokens, these auxiliary depth tokens are just directly added to the image tokens. There's no zero-convey layer in between.
That's right. And their ablation studies actually showed that adding a zero-com here was not only redundant, it actually made things worse. It disrupted the depth integration.
So that tells you the zero-con prick is really specific. It's for injecting these sparse, global, high-level features like pose, not for dense local data like def.
Precisely.
Fascinating. So you have this clever adapter that can handle all these inputs, but to really be omni-modal, the model has to be trained to expect messy, incomplete data, which brings us to their stochastic multimodal fusion strategy.
Yeah, this is so important for making it robust in the real world. If you only ever train the model with a perfect, complete set of cues, it develops a dependency, a crutch.
And then it would fail. The second one of those cues disappears.
It would completely fail. So they essentially train the model for failure. For any sequence of images, they randomly decide how many camera and depth cues are available. How does that randomness actually work in practice? So for, say, a sequence of images, they might randomly pick to provide camera parameters for the first 3 images, but depth maps for 5 randomly chosen images in that sequence.
Interesting. So why is the camera info assigned sequentially, but the depth is assigned randomly?
Well, the sequential assignment for pose mimics how real tracking systems work. You usually have a continuous stream of pose data, but the random assignment for depth simulates things like sensor dropouts or maybe a cheap sensor that only gives you a depth reading every few frames.
So it forces the model to learn how to fill in the gaps itself.
Exactly. It has to learn to fall back on its own internal 3D understanding when the depth cue just vanishes for a moment.
And they added one more safety net, right, forcing 10% of the training batches to be RGB only.
Yep, that's the final firewall. It prevents the model from ever becoming totally dependent on those extra cues. It guarantees OmniVGGT still performs really well, even when it gets no help at all.
Which brings us to performance. If the architecture and training are this solid, did it actually pay off on the benchmarks? Let's start with depth estimation.
The numbers are pretty staggering. In the Centel zero-shot evaluation, just introducing 30% auxiliary depth information led to a 69.71% reduction in the absolute relative error.
Okay, let's quickly define absolute relative error, or ABSREL, for anyone who's not familiar.
Sure, ABSREL is just the average difference between the predicted depth and the real depth, normalized by the real depth, so lower is better. And dropping it by almost 70% with just a little bit of extra info is a huge leap.
Okay, now here's where I want to push back a little. The paper says when you give it 100% depth info, it gets near perfect scores, like 99.9% accuracy. But if you're feeding a model the answer, isn't it supposed to get it right? What does that really tell us about the adapter itself?
That's a really fair question. But the key is the comparison to other models that also got 100% depth input, like a model called POW3R. OmniVGGT blew them away.
Ah, I see.
So it tells us that the Geo-Adapter is just way more effective at fusing that dense input into the transformer. It's not just copying the answer, it's using the depth to constrain and refine its internal spatial understanding.
Okay, that makes sense. Let's pivot to camera pose estimation, which is arguably harder since it's dealing with global parameters.
The gains here were twofold. First, even in RGB-only mode, OmniVGT beat the original VGGT baseline on tough data sets. So the training process just made the backbone better, period.
And second,
when you inject the camera cues, the performance goes through the roof. It outperforms the previous state-of-the-art, POW3R, by up to 16%.
And this is where that engineering efficiency really stands out. We're talking better performance while being 30 times faster?
Yeah, an inference time of 0.2 seconds versus over 7 seconds for POW3R. For any real-time application, like robotics or VR, that's not just an improvement, it's what makes it actually usable.
That's what makes it a production model, not just a research paper.
Exactly. And you see this advantage most clearly on the 3D reconstruction task on the 7 scenes benchmark.
Right, and 7 scenes is notoriously difficult because the camera views are so sparse. There's very little overlap between frames, so standard structure from motion methods really struggle to find correspondences.
It's a classic bottleneck problem. But when they injected the known camera parameters into OmniVGGT on that dataset, They saw a remarkable 65.4% performance gain over the RGB-only version.
Wow, that's massive. It basically proves that the known pose acts like a map for the model. It doesn't have to guess where the camera was, you just tell it, and it can focus all its resources on understanding the geometry.
Precisely. It lets the model completely bypass the biggest challenge in sparse 3D vision.
So let's translate this all into real-world utility. How does this better spatial understanding actually help in a field like robotics?
This is maybe the most exciting part. Because OmniVGGT can generate these richer, more accurate 3D spatial tokens, you can inject them into a vision language action, or VLA, model.
And the VLA needs that reliable 3D context to predict how a robot arm should move, right?
Exactly.
Yeah.
They tested this on the Kelvin Robotics benchmark and showed two things. First, even the RGB-only version of OmniVGGT helped the robot complete more tasks successfully. Second, when you add in the depth queue, the model achieved the best results overall, even slightly beating traditional methods that use heavy point cloud processing.
So it confirms that better structured geometric input directly translates to a robot being better at its job.
It really does.
So to sum it up, OmniVGGT really delivered. It's a single, flexible model that uses whatever data you give it, depth, pose, or nothing at all, while staying incredibly fast and stable, all because of this lightweight Geo-Adapter.
It's a huge achievement. We're seeing these massive capability boosts, solving fundamental problems like sparsity, and all of it was done by adding only 26.8 million new parameters.
And that low overhead is so important. I mean, 26 million parameters is nothing for a huge foundation model, but the fact they kept the adapter so small means you could plausibly run this on an edge device like a VR headset or a robot's onboard computer.
That was clearly the design philosophy. They structured the input really intelligently, using quaternions, for example, so the adapter network itself could be small and efficient.
The efficiency wasn't just a side effect, it was baked into the design from the start, enabled by that zero-con mechanism. And that just leads to the obvious next question.
Right.
If this small, efficient adapter can unlock this level of 3D reasoning in a vision model, what's next?
Exactly. I mean, considering how tiny and effective this thing is, what are the next big foundation models that could benefit from this? Could you inject structured geometric information into a general vision language model to give it better grounding? Or what about a physics engine for a digital twin? Unlocking this kind of spatial reasoning at such a low computational cost. Well, that's where things get really interesting.